method with a particular kind of semantics, you should choose the method a certain way. You know, if you don't, well, you know, you're being the bad guy, right? So, so they have this this kind of way of doing things, which is very interesting. All right, okay. So, you know, this is comparing all kinds of English and Java in all sorts of interesting ways. So now, what about other types of English? So we looked at several different types of English corpora, comparing them with Java. You know, we did Brown, okay, Java, okay. Then we looked at stuff American lawyers write, legal documents, right? So this is, I used to have a patent practice where I helped people sue each other over patents. And, you know, after about a third of my soul got eaten away, I stopped doing it. They pay a lot of money, but they eat your soul. But it's, you know, this is stuff they write, so we collected a bunch of this stuff from that. NASA engineering manuals, okay. And stuff that long-haired dude from Stratford-upon-Avon, also known as Shakespeare, stuff that he wrote. Okay, so we collected all this to see what the statistics looks like. Okay, and did the same study on that. Okay, so that's what that looks like. This is a ZIF plot of trigrams. How many of you have trouble with these colors? I'm just curious. Everybody can see the colors? I guess I'm the only one. I can't actually see these colors. So the top one is, the most repetitive one is Java. The least repetitive one is Shakespeare. Okay, you know. Wherefore art thou wrong? Okay, and the one above Shakespeare is Brown. Okay, and the two really close to each other are law and NASA manuals. Okay, so why is this, right? And I think the arguments are really actually very clear. The same arguments I've been making all along. Is that the harder it is to read, and the harder it is to communicate, the more repetitive it's going to be, right? So, and Shakespeare is a different thing, because Shakespeare is not trying to make it easy for you to read his plays. He's trying to show off, right? He's just trying to show off how many cylinders his car engine has, how powerful he is, right? He just wants to show you. You know, he's like driving around in a Lamborghini Countach and he wants you to know, my car has a louder engine noise than yours. Right? So he's a show-off, right? So he's not trying to make it easy to read. He's trying to be as creative as possible, right? Apart from that, Shakespeare, the rest of it really follows this principle that the harder it is to read, the harder it is to communicate, the more repetitive it is. Any other questions, comments on this? So we're getting close to the end of the science part of the talk. Okay. All right, okay. So, right, so, you know, in conclusion, software is not unique. In fact, it is less unique than English, right? It's much less creative. And so what can we do with this, right? So to repeat the basic pieces of this work is that natural languages are complex, but natural utterances, what people actually say, are simple and repetitive. And so this simplifies speech translation, speech recognition, spelling error correction, and so on and so forth. And we're basically trying to propagate the same ideas to the programming languages. They are complex, but natural programs that people actually write, they're writing them to be read and understood quickly and easily. So they're repetitive, and this can be exploited. Okay, so I have a speech recognition example next. All right, so you're going to hear two short fragments of speech, and they're both going to be noisy, but you won't have any trouble figuring out what that noisy bit is. So first, a speech recognition example, right? So you'll hear a young woman with an American accent, my daughter, saying something, and then you'll have to figure out what it is she's saying, okay?
In Brussels today, the chairman of the European Central announced that interest rates will remain unchanged.
Did you hear that? Ah, what did I just say?
In Brussels today, the chairman of the European Central announced that interest rates will remain unchanged.
So there's a bit of noise in the middle of it. So let me see that again.
In Brussels today, the chairman of the European Central announced that interest rates will remain unchanged.
Okay, how many people thought she was saying European Central Fish? No, right? No, nobody did. Okay, here's another one.
For I equals 0, semicolon, I less than 10, semicolon, plus plus. For I equals 0, semicolon, I less than 10, semicolon, plus plus.
How many of you thought she was meant to say fish? Okay. All right, okay, so you get the point, right? So you knew what she was saying, even though the speech was noisy, no problem for you, right? Okay. And really there's no difference between the code and the English, because both those things you've heard a million times, right? You know what's coming. All right, so this is the point, is that there's a lot of repetition, and these repetitions are going to statistical models, and that makes many kinds of algorithms faster. All right, so we're going to start the rest of this with a little bit of maths review. I didn't know how to calibrate things, so I'm apologizing if this is repetition for some of you, but we'll go through this fairly quickly. All right, okay, so first discrete probability spaces, then some little bit about modeling and what models are and how models work, something about entropy and cross entropy, and then estimation methods. Okay. So, why are we doing this? Well, these are essentially, ideas that are drawn from statistical natural language processing. Remember what Rocco told you yesterday, we all have to learn statistics. I'm convinced that, a lot of the future work in software engineering is going to be from statistical language modeling. And, so I think it's worth your while to learn this stuff. There's a fantastic book. It's statistical natural language processing. The cover is black and white. I can try to find a picture of it and put it up after the break. It's by Manning and Schulze. MIT Press from Stanford. I think it's called the Handbook of Statistical Natural Language Processing or something like that. It's a great book. It's not very expensive, 40, 50 bucks, something like that, dollars. And you can read through it. You don't really need you don't need to take a course. If you can take a course, great, but you don't need to. It's very accessible and readable and very interesting, beautifully written. Lots of great examples. The only risk is that when you read this book, you might stop being a software engineer and switch to natural language. Don't do that. Software engineering is a lot more fun. Okay. All right. So there's a lot of probability in statistics, and most natural language processing algorithms, are some kind of computational way of looking at statistics. So that's why we're sort of going through a quick review of this. All right, okay, so discrete probability spaces. Okay, so in a discrete probability space, you have a set omega of possible events. So, heads of a dice, heads or tails of a coin, so those are discrete probability spaces. And you have a probability function that assigns probabilities to each of those events. The probabilities have to add up to 1. Okay. And so, like I said, the examples are coin tosses, rolls of a dice, and 6-sided dice, and so on. So, in a coin toss, both sides are equiprobable. In a dice, every head of dice is equiprobable. So those are examples of discrete probability spaces. What's not a discrete probability space? What's an example of a non-discrete probability space? Yes, that's right. It's not a trick question. I mean, any other random variable, this heads or tails or ones or zeros, it's a random variable. So any other random variable that takes continuous values is a continuous probability space. So heights of people, intelligence quotients, the temperature tomorrow, these are continuous random variables. Right? And in those cases, essentially, instead of having discrete probability values, you have a probability density function, and you integrate that over all possible values of the random variable, and you get to 1. Whereas here you have a finite set of values that is the discrete probability space and add them up, you get to 1. Okay, so is language a discrete or a continuous probability space? It's a trick question, actually. A little bit of a trick question. Are there a finite set of events in language? Or are there an infinite set of events?
The probability for each word is so obviously discrete.
Yes, it's discrete. Very good. I mean, there's some number of words in English. Usually, most corpuses have around 50,000 different words. In corpuses, well, you can make up words as you go along, but for the most part, once you fix a corpus, the vocabulary is fixed. When you consider sequences of words, there are infinite possible numbers of programs because you could write programs of arbitrary length. Right? Most of the time, you can make it into a discrete probability space by considering finite sentences. Considering the number of 4 tokens, 5 tokens, 6 tokens, things like this, or some other ways of making the continuous probability space. You can make it into a discrete probability space. Okay, so these are what you might call uniform probability spaces, right? Uniform discrete probability spaces. All are equally likely. 6 sides, each probability in a dice. Each side, when you toss it, has a probability of 1/6. Now, English vocabulary, 50,000. Okay. So if I'm speaking and I'm selecting words at random out of 50,000 possible words, which I'm not, then you can think of it as rolling a 50,000 sided die. I have a big die with 50,000 sides, and I roll it. The one that comes up on top, that's the word I'm going to say. I can speak like that. Now, that's not a fair dice, is it? Is it a fair dice? That is, do all sides come up with? No, it doesn't, right? So most of the probability mass in English is on the word the, right? So the is the most probable, and some word like Kelly pigeon or tergiversation is hardly ever used, right? So it's not a balanced die; it's a loaded die. This turns out to be really important, right? So balanced distributions where all the probabilities are equal are very low information distributions, and ones which are very peaky are high information distributions. So we're going to talk about that in a minute. Okay. So words in English are discrete probabilities, but they're very loaded. So some are very likely and some are not so likely at all. Okay. So you can compare different words, right? So the probability of the word the is much higher than the probability of the word bank, right? And and in certain contexts, right, bank and bank, they sound alike, but is there actually a music group called the European Central Band? There should be. So band is, after European and Central, band is very unlikely, right? It's most likely to be bank, right? So the probability of words varies with context, but it's not a uniform probability like rolling dice or tossing coins. Okay. So main concepts here: set of the events. Each event gets assigned a probability. The probabilities add up to 1. Okay. So expected value. So given an event space, any discrete value random variable and the probability p, you can calculate the expected value. Right? So this is in a discrete space. In a continuous space, you integrate the random variable with the density function. All right. Okay. So entropy. So given an event space and a probability p, the entropy of p, entropy of omega, so it's entropy of the whole probability distribution, h omega, is given by the negative log of the log p of e times the p of e. So in other words, the negative expected value of the log of p. So it's the expected value of the log of the negative. Why is it the expected value? Because if you go back and look at the previous formula for expected value, which you've all seen before, it's p. It's the value of this function weighted by the probability. Right? It's the value of this function weighted by the probability. So entropy is simply the negative log of the probability weighted by the probability. Okay? Right. So this is a measure of the uncertainty, the level of uncertainty in the discrete probability space. Right. So if all of the events in the probability space are equally likely, then this value is very high. If it's lower, that usually means that one of them is much more likely than the other. Okay. And this is an important point. So bear with me. I'm just going to quickly do this. Yes. Right. Let me do this. Okay, so I was trying to do this before, right? So let's take a coin, right? And calculate the entropy of a coin. Discrete probability space, two events, heads and tails. Each one is a probability half, right? So let's calculate that. So it's 0.5 minus 0.5 times log of 0.5 to the base 2 plus, well, it's minus again, minus 0.5 log. Right? So everybody see that's the entropy of a coin toss? Is that clear? Yeah? We'll make sure everybody's on board here. Okay, all right. So that's going to be 1 bit, right? Because the coin toss is exactly 1 bit. 1 bit of information, right? That's what it's toss. That's the most a coin toss can have, right? So now let's consider a coin that's not a fair coin, right? So a coin that one is more likely to come up than the other. Let's say it's 0.75, so the head is heavily weighted, right? Is that right? Okay, so head's much more likely, so the calculating the expected value by weighting the head more. Yeah? So this is going to be less, because this coin has less information. Because more of the time it's going to come up heads. So there's less information, right? So if you make it really biased, it's going to be even less information. Even smaller amount of information, right? So you make it super biased. So this is the kind of odds you have when you play the stock market, because it's so rigged. It's almost negligible amount of information, right? So what happens if we do this? Supposing we know that it's never going to come up tails. What should happen?
Zero.
I think we're going to be sent to jail. Okay, so where do we get that? Where do we get not a number? Okay, so for this purpose, by calculating entropes, 0 times log of 0 is defined to be 0. Right? So it's just a mathematical thing that we do when we calculate entropies, is that 0 times log of 0 is taken to be 0. So in that case, we will end up with 0, right? Because log of 1 is going to be 0, right? So in fact, you can see this if we just do this. Okay, so, as n tends to 0, you'll end up with 0. Okay, so what that means essentially is that if you have a heavily loaded coin where you know that one of them is going to come up most of the time, you're going to get an entropy very close to 0. So you think about dice, for example, a 6-sided dice. If it's loaded so that one face is going to come up most of the time, there's basically no information in the dice. The 6-sided dice. Now consider this 50,000 sided dice, which we call English, where the most common word is the, right? How much information is there? Whereas a different kind of 50,000 dice where every side has an equal probability of coming up, right? So if you have a 4-sided dice, I don't know, it's hard to imagine, supposing you had a 4-sided dice, there's 2 bits of information if every side is equally likely, right? So if you had a 50,000 dice, there's log to the base 2 of 50,000 potential bits of information there, right? So log to the base 2 of 50,000, how much is that? Okay, 15.6 bits of information, right? So each word of English potentially could have 15.6 bits of information if all sides are equally likely. Is it going to be less than that or more? Much less, right? Because most of the words in English are the. So it's much less information. And we'll see this, right? So eclipse, for example, right? if you take all the Eclipse, the vocabulary is somewhere in the region of 200,000, something like that, 200,000, maybe 300,000. Right? And how much information is in 200,000 or 300,000 almost, right? 17 bits. Much less information. Eclipse is basically non-informative. You might as well not read it. There's nothing there. We'll see. All right, okay, so let me get back to talk. What is it doing? Okay, a little bit of a detour into entropy there. Right, so yeah, so that's entropy. So hopefully people got the idea of distributions, event spaces, and skewed distributions and uniform distributions. So uniform distribution has the highest entropy, but we never see that in natural language or in code. Okay, conditional probability. So often arises out of partial knowledge. So you have several events that occur together, and maybe you know some of them, you don't know the others. Right? So, for example, I don't know what tomorrow's weather is, but I know what today's weather is. So it turns out tomorrow's weather is very dependent on today's weather, so it's a conditional probability. Okay, so you have events A and B, and you have the joint probability of occurrence. It's sunny today, and it's sunny tomorrow, for example. So I guess it's like California here, it never rains in the summer. Is that the same here? Does it ever rain here? No? It rains. So, yes. So you can think about conditional distributions. So given that we know what the weather is today, what is the event tomorrow? So conditionally, what's the probability of B given the probability of A? And so we have conditional probability equations. So P of joint probability of A and B is the conditional probability of A given B times the probability of B, and likewise everything else. And this gives rise to the famous Bayes equation, where you can invert it to, and we'll see that later on as well. Okay, and then we have the chain rule, which is very important in natural language modeling. If you generalize from AB, probability of joint probability of A and B is probability of A given B times probability of B, and likewise with that. You can take the joint probability of a whole lot of events, right? So think about all the words that occur in a corpus. If you think of it as one joint probability of all the 50,000 words in the sequence that appear in a sentence or in a program, and you can make each one, the first one you can make an independent choice, the second one you can model is dependent on the first, and the third one you can model is dependent on the first two, and the fourth one is dependent on the first three, and so on. So you can write out all the probabilities in this way. So this is called a chain rule. Okay, so we're gonna get into more about how all this works out. So the thing is, all these things in natural language processing and many other fields in empirical software engineering, these probabilities, they're just models of an uncertain world, right? So in general, when you talk about linear regression, it's a probabilistic model. When you talk about population parameters like the t-statistic, or the effect size, the Cohen's d effect size. These are parameters that we estimate from a sample, right? So these are sample parameters, and they're uncertain models of the real world, right? So we calculate the sample mean, or sample average, or the sample standard deviation. These are all some things we imagine and somehow represent the real world. They're uncertain. They're models of an uncertain world, right? So it's the same thing with discrete statistical models that are used in natural language processing. They're all estimated from some corpus, something we've already seen, and they're sort of imperfect models of what actually exists out in the world, either the language phenomena that obtain in the real world, or the code that people write. So they're sort of imperfect models. Right? So when we as engineers work with imperfect models, we have to have some way of characterizing what is the level of imperfection, how good is it, how bad it is. And we need to know that because we're constantly trying to make our models better. Right? So the better our models, the better our tools will perform. Right? The better understanding we have of the world, and so it's always a struggle to try to find the best models we can. Right? So when we think about discrete models like we use in natural language, it's always trying to assign a probability to a statement, to a programming language statement, or or the best patch for a bug, or the best translation of a particular program in Java to a program in C#. So these are all probabilities we're trying to assign. And we want to get the best probability we can, but we do all this by building models, mathematical models of what these probabilities are. So, so this guy is, George Box. He's one of the most famous statisticians ever, and he's known for this statement, famous statement that says that all models are wrong, but some are useful. So no model is perfect, right? So even Newton's laws of motion are not perfect. Even Einstein's equations are not perfect. They're all imperfect models, understandings of the real world. What is surprising is that how well they work. That's what's really surprising, right? So there's a beautiful essay called "The Unreasonable Effectiveness of Mathematics in the Physical Sciences." That's the name of the essay. It's a wonderful essay worth reading. Unreasonable Effectiveness of Mathematics in the Physical Sciences. So all these things we do are wrong, but some of them are useful. We have to figure out how wrong it is, right? We have to figure out how good it is. We have measures for measuring how good our models are, right? So we're going to come up with these measures for these language models called cross-entropy, which is based on entropy. So, but this is an important concept that models are necessarily wrong. In fact, this is, if you read the Bible, this is the first commandment, right? The first commandment says, "Thou shalt not make graven images of me." Is it the first or second commandment? "Thou shalt not make graven images of me." I take that to mean, don't confuse models for reality. So I think that's really what the prophet meant. I think that's really what Moses meant. Is that don't confuse, what images you make for what the reality is, right? So that's exactly what this is saying. So all models are wrong. Don't believe it. Okay. So the question is, how do we know when one model is better than the other? Right? That's all we can do. We can compare models and try to see when it's better. Okay. So a typical approach that that happens in these settings is we have some data, right? We get this data from somewhere, and it all depends on the setting. And from this data, we estimate a model. Okay. So the model might be just simply modeling the data, like you're building a regression model. The regression model, you have a variable that's dependent on a bunch of other variables, and you make some assumptions that that it really fits some sort of linear regression line, and that the residuals are normally distributed around the regression line. You make assumptions and you fit a model that tries to make that as well as it can. In some other cases, you have labeled data. You have, this is a defective file, this is not a defective file, and you're trying to build a model that predicts which files are defective and which files are not. So, in general, given labeled data or some other kind of data, you build
That was very important matter. No, can we stop kind of?
Sure, yeah.
Because I think that today we go for practice at 10, so I don't know if they are waiting
Okay,
there.
I'm happy to stop now. I'll just start with this slide over again, what models.
Okay.